Let us start lecture 28. We will continue our discussion on passivation and mixed potential theory. In the last lecture, we could see there are three situations which are pertaining to the interaction between cathodic polarization and anodic polarization, and here we are considering the anodic polarization to be active passive mode. So, we can have spontaneous passivity, we can have active passive transition, and as well as we can experience cathodic loop, which talks about the unstable passivity achievement. Now, we will talk one important aspect, influence of I critical as well as EPP and ECP. So, these three points are very critical. Of course, when we talk about CP, it is automatically coming up with, because these two are in combination and ECP and IP are in combination, because if we see the passivation active passive plot for dissolving metal. So, this is the plot, and every time we are considering transpassivity. So, this is transpassive, this particular zone is passive, and this is EPP, and this particular current is I critical, this is I passive, this is ECP and this is E trans. Fine, these are the points we are talking about. Now, so this is complete passivation potential, this is primary passivation potential. So, if we see the interaction, let us say I see an interaction like this, this is the plot of anodic side, anodic part. Now, if this is my cathodic line, okay. So, this is my cathodic line, let us say, and then in this particular situation I will get spontaneous passivity, because the system will reach to this potential which is E mix. Now, if we reduce the concentration of the oxidant, so this is E, let us say oxidant, E ox, and this is E of metal, dissolving metal, E equilibrium of the metal, this is E equilibrium of ox, or I can write it like this, oxidant. So, this oxidant concentration if we reduce, so then this point will shift downwards. Why? Because if we consider ox plus E equal to red, oxidant plus E equal to reductant. So, my E ox red equal to E naught ox red plus RT F ln concentration of ox and concentration of red or reductant. This is ox is basically oxidant and this is reductant. If this concentration reduces, so I can have a situation like H2 H plus E equal to H2 to this particular case, this is oxidant. If this concentration reduces, so I will have, since this is reducing, so these value will go down. So, this potential will go down. So, if this potential goes down, but the slope, this is beta c, if it does not change, this line will move like this. It will be 1, and this, if you further go down, it will be like this. Fine. So, these are the 3 situations I am considering. This is the situation with a concentration C1, this is C2, and this is, let us say, C3, and of course, our concentration relation would be C1 less than C2 less than C3. So, now if we start with C1, the system will reach at this point in the free corrosion condition without having any influence of external current. Now, in case of C2, the situation system will reach here, okay, which is exactly, so this is I core 1, this is I core 2, and this becomes, and once we increase the concentration from C2 to C3, my I core moves to this point, which is I core. So, this particular situation where the concentration reaches C3, that time this particular point becomes my mixed potential point, where this mixed potential theory is satisfied. So, this is nothing but I p, this is I p. Now, interesting part is, this case the metal is freshly prepared without having any oxide surface on that particular metal. So, when we have this interaction between 2 equilibrium potentials, they will try to take the potential, final potential in between these 2 extreme potentials, and since it is freshly prepared. So, when the concentration is C1, that means this is C1, the corrosion rate would be here, and when the concentration is C3, the corrosion would be here. Corrosion rate will be at this point, because that becomes my mixed potential theory. So, it is very clear that this polar concentration, this cathodic polarization line must cross this I critical. This is basically this point, it must cross to get to the steady state passive region. So, this particular, this I critical is limiting to achieve steady passivity. So, I critical is limiting for the attainment of passivation, and here the passivation is stable passivation. Fine. So, the concentration of that oxidant should be such that it just crosses this I critical. So, this C2 concentration, at C2 concentration, this cathodic polarization line is just crossing, just touching the I critical point. So, there I will not have stable passivity. So, once it crosses that, I will get a stable passivity. So, if I critical increases, I would definitely, it will not be a very good system for the attainment of passivity. Stable passivity. Why? Because if I extend this I critical point, so if I extend it, so if it reaches there, so then if I do not change the, let us do it with the blue color. So, if I extend this I critical point, and without changing the I passive region. So, now the new I critical is this, and in case of I critical in the previous instance, at least C3 composition, which is this is C3, was giving me, allowing that system to attain stable passivity. But once this I critical new has been considered, that means in a system where I critical is very high, even with the C3 concentration, which is pretty high concentration in this comparison to C1, it will not give me stable passivity. So, for a system to be a very good passivating metal, it should have a lower I critical, it should not have a very high I critical. Similarly, if I try to look at this gap, the gap between E equilibrium metal and EPP. So, here I am just drawing this EPP as well as ECP at the same level. So, this gap, if it extends, that means if this gap increases, so that means if ECP or EPP minus E equilibrium metal, this difference, if this is del E1, if it increases, that means this is also not good, because if it increases, even with the the condition of constant I critical, the situation would be very different. So, in case of I critical, in terms of getting a stable passivity, one should have a very low, that metal should possess a very low I critical in that passivating medium, and if it increases also, it will lead to affect the passivity in a negative fashion. Why? Let us see that particular influence. This becomes my log I and E volt. One case I get a plot like this. So, this is my E ox and this is or E equilibrium ox, and this is E equilibrium metal. So, this becomes my E mix when I will have this particular very situation where it just crosses I critical, this I critical. So, in this case I will have stable passivity. So, here correspondingly I could get I core, which is nothing but I passive. Now, if this particular difference increases, keeping the I critical constant as well as IP constant, the IP and I critical, they do not change. So, what will be the situation? So, I change that particular, so if it is coming here and then if the pattern is this, if the pattern is this. So, that means I am not changing I critical remains same. So, in these two plots I critical remains same, IP same, or I would say no change. I critical, IP, no change. Only change is in del E1, which is the difference between EPP minus E equilibrium M. So, this point belongs to EPP and here it is EPP. This is case 1, case 2. or this is case 1, this is case 2, fine. So, in this case if we consider case 1 is less than del E 1 case 2. So, in that situation when we go to this, I get stable passivity and here I get unstable passivity, since in this situation I will get cathodic loop, fine, but here I will get spontaneous passivity. Okay. So, that means it is very clear, and also correspondingly I could see the ECP effect. So, this is ECP, this is ECP 2 and in this case it is ECP ECP 1. So, I could also correspondingly see the effect of ECP also, ECP. So, ECP should be as close as EPP. So, that will help us to get to stable passivity also. Now, these are the two influences, that means the effect of position of EPP and I critical. So, this should be as close as E equilibrium metal, which is reversible potential, this potential. At the same time, I critical, if I try to see the I critical condition, it should be as low as possible. So, these two situations I would get stable passivity, and under this circumstance, because the polarization plot for the cathodic side is cutting across the anodic part in the passive region. So, I would get spontaneous passivity or spontaneous passivation is possible. Now, let us look at the influence of IP. Okay. So, influence of IP. So, the influence of IP is very clear. For example, if we get a mixed potential theory log I and this is E volt. So, if I try to plot if I try to see these two plots, one case it is and both the cases this point is maintaining. So, this two different colors are indicating let us say this is metal 1 and this is metal 2, and if the cathodic polarization line is like this, is like this. This is the cathodic polarization line. Okay. So, I could see the both the cases I would get. So, in this particular situation the stable passivity will get for both the cases. So, this is for metal 1, this is for metal 2. So, stable passivation is achievable for both the cases. Is possible. Okay. So, if we do not have any change in the I critical or I critical as well as this gap maintains same. So, the daily 1 as well as I critical remain same. So, that case I could achieve stable passivation in both the metals. But the major problem appears when we start decreasing the concentration of the oxidant. So, this particular potential will start going down. So, when it goes down, it will go like this. So, if I try to look at with the, so this will go down like this, let us say. And in this case there is another solid line I am drawing. So, when the concentration goes down like this, so that means this is 1, this is 2, this is 3, this is 4, this is 5. So, and all those corresponding to C1, C2, C3, C4, C5. So, these are the concentration and the relation is C1 greater than C2, greater than C3, greater than C4 and greater than C5. Interestingly, if I look at when we achieve this particular passivation point, once we achieve this particular passivation point, then if we reduce the concentration, okay, so the passive layer now has formed. So, if we do not disturb the passive layer in the form of scratching or let us say increasing the turbulence in the medium, so that the oxide layer gets dislodged from the surface, that means passive layer is dislodged. So, if we do not do all those things unless we cross this particular point for metal 2 and this particular point for metal 1, I would keep the passivation will be maintained. Okay. So, now in case of metal 2, I could maintain the passivation till concentration C4, okay, till concentration C4, that means in this concentration for metal 2 passivation is maintained. But once this concentration goes to C5, that means the concentration reduces, that oxidant concentration reduces, the line becomes C5. That case, that C5 cuts the polarization anodic part of the M2 in the active zone. So, this is the cutting point. So, the passivation will be lost and then metal 2 will dissolve in the active fashion. But if we consider M1, this M1 for the metal 1 till it reaches C5. So, that means it is just touching the corner point, this corner point, till that C5 it will maintain its passivity, but once we cross C5, let us say the C5 is crossed, that means C6, if I consider C6. So, C6 points let us say here. So, we will have a polarization plot like this, where it will cut here in case of metal 1 and the metal 2 also, this is the point. So, which is for metal 2. So, both the cases now passivity will be lost, but interestingly metal 1, if I compare the passivity, metal 1, IP of metal 1 is lower than IP of metal 2. So, when we reduce, after achieving the passivity, stable passivity, if we reduce the oxidant concentration, then until unless that cathodic polarization line crosses the IP point, which is basically the CPIP point, ECP. So, this point corresponding to ECP M2, this point corresponding to ECP M1. So, that point until unless that cathodic polarization line crosses, we will not be able to break the passive layer, provided of course, in case of in between C1 and C3 for M1, M2 for M2, in between C1 and this range, if we do not disturb it. If we disturb it, the situation will be different, we will talk in the next lecture, but if we do not disturb the passive layer, in case of M2, C3 is the critical concentration corresponding to IP of that M2, and C5 is the critical concentration for metal 1 corresponding to IP metal 1 or corresponding to ECP of metal 1, and this is in this M2 case, this is ECP metal 2. So, it is very clear that if IP is less, in other things are same, so that particular metal would have a better possibility of getting to a stable passivity and maintenance of stable passivity. Okay. So, this is one critical aspect. So, that means in order to have or criteria for passivity, IP should be as low as possible, and correspondingly. So, that means if we combine all the other situations, so IP should be low, I critical should be low, as well as EPP minus E equilibrium, this gap should be low also. So, those situations I could achieve passivation very easily, provided the cathodic polarization line is positioned same fashion in all the cases. So, this is the criteria for stable passivity, and when we talk about IP, I am discussing also, I am taking part of ECP. When I am talking about I critical, I am taking consideration of EPP also. So, let us stop here, we will continue our discussion in our next lecture on this very aspect of passivation and its interaction with the cathodic polarization line, this anodic polarization and cathodic polarization line in the passive zone, as well as if we go away from the passive zone. So, thank you very much. We will continue in our next lecture.